In this video, we are going to talk about how to tune model parameters to meet design specifications and goals using Simulink Design Optimization. Specifically, we will talk about what is Simulink Design Optimization, how would you select design parameters, setting requirements or design goals to satisfy, and finally, optimizing model parameters. We will use a suspension assembly similar to what we have developed in previous videos. There are two additions in this model when compared to previous videos. Firstly, this model has the left wheel suspension system also assembled. Secondly, the spheres here represent the roll center and the instantaneous centers of the vehicle. These are interesting quantities to look at when designing suspension mechanisms and could be used to tune our suspension parameters. Given that we have this configuration, let's take a look at the example suspension design goals or requirements for our model. First goal is to constrain the camber angle of the wheels between -1 and -7 degrees. Camber angle of a wheel is measured with respect to the vertical. For the left wheel, positive camber looks like this, and a negative camber looks like this. A negative camber gives the car better grip when cornering, so that is what we would be optimizing for. To be able to optimize the camber, we need to measure the camber angle first. Let's switch to MATLAB to see what this looks like in our model. Let's open the model Suspension SDO. Here we see the chassis subsystem, the left and the right wheel suspension subsystems, and the left and right test force subsystems. Apart from this, we also see a camber subsystem. Let's double-click on it to access its contents. This subsystem calculates the camber of the wheels. Here we see that the angles measured elsewhere in the model are visualized. Let's double-click on one of the from tags to access the go-to source here. So let's click on this hyperlink to see where this signal originates from. Here we see the camber angle is directly measured using the transform sensor block that we discussed in the previous video, Building Mechanical Assemblies Part 2. Let's go back to the presentation. So constraining the camber angle between -1 and -7 degrees is the first goal. The second goal is to constrain the roll center height to less than 150 millimeters or 0.15 meters. Having a lower roll center has several advantages, one of it being higher traction. To be able to optimize roll center height, we need to be able to measure it. Let's switch back to our model to see what this looks like. In our model, let's update our model using the shortcut Ctrl-D to bring up the Mechanics Explorer. Let's switch to the right view and then simulate our model. We can see the wheels undergoing force tests similar to the Building Mechanical Assemblies Part 2 training video. Let's pause this animation a bit. Here we see the roll center and the instantaneous centers. These are a function of suspension geometry and are calculated by solving trigonometric equations. For example, this instantaneous center is the intersection point of these two imaginary lines formed by the suspension arms. The roll center is the intersection of these two lines. Please refer to the links in the resources section to see how to derive these equations to compute these center locations. To see how the center location calculations are implemented in our model, let's go back to the top level of the model and then access the roll center subsystem. For the camber angle, it was a straightforward measurement using the transform sensor block. We can also perform elaborate calculations using MATLAB function block and other Simulink blocks to calculate the quantities necessary for our optimization. For example, using MATLAB function blocks, we solve for the trigonometric equations based on the parameters measured in the rest of the model. Here we see the measured parameters A, B, C, D that are the component positions of the suspension assembly. Let's take a look at one of the MATLAB function blocks by double-clicking on it. Here we see the measured parameters, and we solve for the center position using the backslash operator. Please refer to the documentation to get more information about the backslash operator. Let's go back to the model by clicking on the Go to Diagram button. We first calculate the instantaneous centers and use it to calculate the roll center. We then visualize these quantities using the visualization subsystems. Let's double-click on one of the subsystems to take a look at its implementation. So for example, let's click on the roll center visualization. We simply feed in the center position and actuate a solid sphere through a planar joint to move it in the YZ plane. Note that the visualization subsystems are individual mechanical systems by themselves that are used only for the visualization and do not have any effect on the rest of the suspension system. Let's go back to the top level of the model. We are going to use this simple parameterized model to set up our optimization. Now that we know the design goals, namely the camber angle goal and the roll center goal, we need to decide on our design parameters. These parameters will be the answer to the question, what parameters do we change to achieve these design goals? Let's go back to our presentation. We will choose the following two design parameters. The first one is the position of the connection point between the upper arm and the chassis. This is controlled by a distance variable that specifies how far the upper arm is positioned from the chassis' center of gravity. The second parameter is the upper arm length itself. We can see that changing the value of these variables will change the geometry of the suspension system, thus having an effect on both the camber angle and the roll center height. Note that these are example parameters to tune for our particular example design problem. For any other application or a different design problem, the workflow to perform design optimization would still be similar even though the parameters to tune and the goals to reach could be different from this example. Next, we need to set up the optimization problem using Simulink Design Optimization. There are two types of optimization-based techniques, both of which use Simulink Design Optimization. Parameter estimation. Here, we use experimental data to fit model parameters. The goal is to improve our design such that the simulation is more likely to match the data provided. Response optimization. Here, we use performance metrics as cost functions to tune algorithm parameters. Examples include constraining signals within bounds, reducing settling time, overshoot, etc. Please note that these techniques can be used to tune both plant and algorithm models. For our example here, we are not going to use experimental data. On the other hand, we are going to constrain the roll center and the camber angle using response metrics. So we will use the response optimization approach. The diagram to the right shows how Simulink Design Optimization works. The optimization routine begins by simulating the model with a set of initial values for our design parameters such as the suspension upper arm length. The model outputs are evaluated against user-specified requirements, in our case, the camber angle and the roll center design goals. This produces a cost function which must be minimized. As long as the optimization criteria have not been met, the model parameters are modified based on the optimization routine and simulation is run with new values and the cost function is evaluated again. Now that we know how Simulink Design Optimization works, let's switch to MATLAB to see how we can do this. In our model, start a response optimization analysis by selecting the Analysis menu and Response Optimization. This opens up the Response Optimization tool. We will start off with the variables and the requirements sections to define which variables will be used for the optimizations and what requirements to satisfy. To define which parameters are tunable by the optimization algorithm, select New from the design variable set here. Let's select the design parameters to be tunable. To do this, find our variables. In our case, it's going to be arm1 chassis distance, which is this parameter, and arm1 length, so we can use Control-click to select multiple parameters, and click on this arrow to add it to our design variable set. Note that these variables control both the right and the left upper arms of the suspension system to maintain symmetry in the model. We can also see the current value described by our MATLAB-based workspace here. These will be used as default initial values for our parameters. We can also see the default minimum and maximum values for our parameters. All these values are editable. It is recommended that we provide meaningful minimum and maximum values for the parameters to restrict the search space. For example, let's switch to our Mechanics Explorer. We might not have full freedom to place this point anywhere on the chassis because we are constrained by the chassis design. So let's restrict it to between 5 centimeters and 15 centimeters. Similarly, the arm length itself needs to be constrained by factors such as track width, competition rules, etc. Here, let's specify the minimum and maximum to be 20 and 50 centimeters respectively. So let's go back to the response optimization tool and specify our minimum and maximum values. Select OK to save changes. We can see the design variable set has appeared here. Double-click on the design variable set to take a look at the description. So here we see the two variables, the minimum, maximum values, and the current value. Next, we need to define the requirements or design goals for the optimization to match. First, let's set the constraint for the camber angle. To set response requirements, go to the Requirements section and select New. We can see several different options under Time and Frequency domain. Some examples are Step Response Envelope, Custom Criteria, Natural Frequency, etc. For our application, we will choose the signal bound criteria since we are constraining a time domain signal to a particular value. Let's select this option. We will set the signal bound for the camber angle upper bound first, so we can call this camber upper bound. We can set the signal bound properties in the Specify Signal Bound dialog. Here, let's constrain the signal to be less than equal to the bound because it's the upper bound. Now we will specify the time and the amplitude properties of the signal bound. Here we will set the time start to 5 seconds and the time end to 55 seconds. Since we don't want to include the part of the simulation where the suspension system is initializing or setting to the final stage. Let's set the amplitude to -1 degrees, which is the upper bound. Now that the properties are specified, we need to choose a signal to bind with these specified characteristics. We can do this using the Select Signals to Bound dialog. Click on the plus button to create a signal set. Let's call this signal set camber. Then select the signal that represents the camber angle measurement from our model. To do this, let's switch to our model, access the camber subsystem, and choose one of these signals. Since our model is symmetric, it doesn't matter which signal we choose here. So let's go back to our response optimization. We see the signal appear here. Select it and say OK to see the camber angle signal here. Click OK. We can see a time plot popping up with the specified constraint. We don't see any signals here because we have not yet run the simulation. We will do this once we have set all our design goals. Next, we need to set up the camber lower bound. To do this, we will go to the new option under requirements again. This is also a signal bound. Let's set the name to camber lower bound. And we will specify the characteristics here. We will constrain the signal to be greater than or equal to the bound because it's the lower bound. Use the same time range, so 5 to 55 seconds, and set up the amplitude as -7 degrees, which is the lower bound. The measurement signal is going to be the same signal, so we will select the camber angle here. Notice that we have an option to create a plot. Let's uncheck this option and select OK. Now we don't see a time plot that corresponds to the constraint that we just created. This is because we wanted to add the lower bound constraint to the same constraint plot as the upper bound constraint here instead of creating a new plot. We can do this using the plot section. Select the data to plot. So in this case, it's going to be the camber lower bound. Go to the add plot option and choose the time plot 1. Now we see that both the requirements appear on the same plot. That is our first design goal. The second design goal is to set up the requirement for the roll center. To do this, we will access the requirement section and click on New again. This is also a signal bound criteria since we are binding the roll center to 150 millimeters. So select the signal bound option again. We will specify a name. In this case, let's call this RCB for the roll center bound. We will set the signal bound to constrain the signal to less than equal to the bound because it's an upper bound. We will set a similar time range. So in this case, start time is 5, end time is 55. For the amplitude, we will choose 150 millimeters. Since our measurements are in meters, we will specify it as 0.15. Next, we need to choose a signal to bind these characteristics with. We currently have only the camber signal. We need to create a signal set for our roll center height. We will click on the plus button again. We will call this the roll center signal set. Go back to our model and access the roll center subsystem and the roll center visualization subsystem. Select this signal, which stands for the roll center height. Go back to our response optimization to see that the signal has appeared here. Select the signal and say OK for the roll center signal to appear. We would like to create a new plot for this signal constraint to appear, so select OK with the create plot checked. This is our second and final design goal. Note that we are not specifying a lower bound for the roll center criteria. This is by choice. The rationale is that we would like to know the lowest roll center position possible for our current configuration. In reality, we might need a lower bound for the roll center as well, so that the optimized roll center is not so low that the chassis might actually hit the ground. Sometimes it's a good idea to optimize for lesser parameters with less stringent bounds to see how the algorithm performs. Next, let's go to the View tab. Here, we can explore the layout options. For example, we can make the two plots appear on the left and the right hand side simultaneously so that it's easier for us to monitor the results. Let's go back to the Response Optimization tab. The next step is to plot the model response. To do this, we can click on the Plot Model Response button. The tool then runs the simulation and then plots the results. We can see the two plots, namely the camber angle and the roll center here, and determine that the current parameter and configuration does not satisfy our goals. The next step is to optimize these parameters based on our design goals that we have set up here. To do this, click on the Optimize button. We can see the optimization progress report pop up that will give us information about the iteration details. The tool runs the model, evaluates our cost function based on the design requirements that we have set, changes our selected design parameters based on the default optimization algorithm, and then runs the model again until the goals are met, or another termination condition such as the limit on the number of iterations is reached. Note that based on the application, the number of parameters to be tuned, etc., the time to reach the termination condition will vary. We see from the progress report that the optimization has converged and was successful. Let's go back to the plots. We can see the signal values for different iterations. The blue plot is the final optimized response, and we can see that it is within the signal bounds, so the optimization was successful. The final value of the optimized response can be accessed by double-clicking on our design variable set. These variables are also updated in the MATLAB base workspace. Recall that the initial value for the chassis distance parameter was 10, and right now it has converged to 11.8. And the initial value for the upper arm length was 40, and it has converged to 38.8. Let's go back to the Mechanics Explorer to take a look at the final configuration. Let's update this model. This is our final configuration. Let's compare it to the initial configuration. We can see that the upper arm length is reduced, resulting in the wheels pointing towards the suspension, resulting in a negative camber. Based on our distance variable, the upper arm connection is also a little towards the top. Let's simulate the model for the optimized configuration to take a look at the final results. We can see that the roll center is also in a lower position. Let's go back to the response optimization tool. Let's talk about a couple of options here that will help you with your design optimization workflow. The file options here allow you to save and open existing sessions to continue your work. The options here allows us to tune several optimization options to work better for our application. Click on it to access all the options. For our example, we could change the method used for the optimization. We were using the default optimization algorithm. We could switch this to simplex algorithm, for example, since sometimes it has a lower likelihood of being stuck in a local minimum at the expense of, however, taking longer to complete an optimization. Note that both the gradient descent and the simplex search algorithms are local optimization techniques. In other words, these algorithms return only the local minima. For the local optimization algorithms, it is very important to specify a good initial guess for our parameters. Generally, initial guesses are based on design thresholds, domain expertise, etc. Running Monte Carlo type simulations for a range of parameter values is a common way to understand the effect on the model for a given parameter. This also helps in providing better educated initial guesses. The pattern search algorithm, however, is a global optimization routine. Apart from this, parallel options help us speed up optimization routines by using parallel computing on multi-core processors. Please refer to the documentation by clicking on the Help button to get more information about all these options. Let's go back to the presentation and do a small recap. We first set the design parameters for our problem through the variables section. We then chose the required variables. First, we chose the ARM1 chassis distance parameter. This was used under the chassis subsystem. We also noted that it is recommended to provide min and maximum values for the variables. We did the same thing for our second parameter, namely the arm length. The arm length parameter was used in the arm solid block. We provided the minimum and maximum values for this variable as well. Next, we set the requirements and design goals. We did this through the requirements section. There are several available in time and frequency domains. We wanted the camber angle to be constrained between -1 and -7 degrees. So we chose the signal bound. We specified the time and amplitude ranges for our constraint. We then chose the signal to bind with this constraint from our model. We then wanted to constrain our roll center to 150 millimeters. So we chose the signal bound again. We specified the time and amplitude ranges for our constraint. We then chose the signal to bind with this constraint as well. Finally, we click the Optimize button to run through the optimization and get the final design parameter values that satisfied our goals. We also talked briefly about options you can set for our optimization problem. In summary, we introduced Simulink Design Optimization. We saw how to set design parameters and requirements, and finally optimize model parameters. This concludes this video.